Hey folks, welcome to the second video for 3.1. This video is all about gravitational potential energy. You will definitely want to pay closer attention to the first half of the video because you will spend a lot more time with that content than the second half of the video. We start with gravitational potential energy near Earth's surface. The definition here is energy stored in a system due to gravitational attraction. I have this diagram here showing a person on a table in a room holding a ball to show the different decisions you can make with gravitational potential energy. But first, I want to focus on this idea of stored due to gravitational attraction. Now, gravitational attraction is the gravitational force. And we studied forces for a while, and one of the things that we learned about is that in order for there to be a force, there has to be two objects interacting. So in order for there to be potential energy, there has to be two or more objects. Oh, that's not the word object. Objects. A single object, in other words, can't store energy with itself because it can't exert a force on itself. For potential energy to exist, there has to be two objects or more so that there can be a force of interaction between them. The equation definition in your equation sheet for gravitational potential energy is delta UG equals mg delta y. Which is not how I would recommend using this equation, but it does give us a very important idea in the world of energy, and the idea is that energy is relative. When we define like the kinetic energy of an object, we define it based on the fact that an object that's not moving from our perspective has a kinetic energy of 0. But if you think about what Earth is doing right now, every object on Earth is moving right now. It's moving from place to place because the Earth is rotating. And so even if there's a water bottle at rest on my desk, it technically has kinetic energy because it is moving within the universe. So we have to be careful with energy and think only about how much energy something has relative to something else. So that's why there's a delta in this equation. The difference in gravitational potential energy between 0 and some value is based on the mass, the value of little g, and then the delta y would be like the vertical displacement. Now, mg is there, and it maybe is no surprise because we're talking about the force of gravity. So this equation relies on you making a physics decision. There has to be somewhere in your perspective a place where the gravitational potential energy is equal to 0. That is going to be when the vertical position is 0 meters. Quick side note, your textbook uses PE a lot for potential energy, which is super common. The AP Physics 1 equation sheet uses U as the variable for potential energy, and then the G subscript to denote gravitational potential energy. So I want to end this part by talking about this picture here, and I have the ball at a specific height above the floor, also a specific height above the table, and a specific height below the ceiling. So these variables are y1, y2, and y3. And so I'm going to use these heights to kind of demonstrate how you would need to think about potential energy. You have to decide where this point is. So you actually get to choose. Not only do you get to choose, you have to choose where in your picture there would be 0 gravitational potential energy. And I present to you 3 choices for this room. So we're going to set up a little kind of a chart. If UG equals 0, and then we'll say at the floor, on the table, or on the ceiling. We can write 3 different equations for gravitational potential energy just based on those 3 decisions. So in my first go through here, I'm going to say that y equals 0 at the floor, and that is where there's 0 gravitational potential energy. Well, that means that there is a gravitational potential energy of the ball stored with gravity that's equal to the mass of the ball times g times the vertical displacement above the floor. Well, according to my measurements, that's going to be y1 plus y2. It's the distance from the floor to the ball, because I decided that 0 potential energy was at the floor. And maybe there's a good reason I do that, but maybe there's not. If instead I decide that there's 0 gravitational potential energy on the table, in other words, my toes would have 0 potential energy, then my gravitational potential energy equation would become m times g times the height of the ball above the table. And so that would just be y2. Those are the most logical decisions to make. Now, you can make any decision and physics will still work. So if I decide that there's 0 gravitational potential energy on the ceiling of this room, then the gravitational potential energy of the ball, based on the force of gravity, is m times g times the height above the ceiling. Well, the ball is not above the ceiling. It's below. And so the height above the ceiling is negative y3. That's an important thing to realize, that you can actually set up a frame of reference where there's where there's negative gravitational potential energy. I don't recommend doing that for many things, but it is possible. There is like a usual way to do things. Usually set gravitational potential energy equal to 0 at the lowest point. And I will try and talk about that as we go through some example problems. You can get creative with that, and it can actually solve a lot of problems easier for you. All right, so that kind of ends the important part. This next part is going to probably sit uncomfortably with you because I'm going to skip the reasoning behind it. But we use this equation that we just learned. We can use it only if the value of g is constant. And so we can use that on the surface of the Earth or near the surface of the Earth because, relatively speaking, the value of little g is constant. But if we are in space, where we are far from a planet's surface, we need to use a different equation. And so we have ug equals negative big G, big M, little m over r. And there's some like wacky stuff happening here. This equation has a negative sign, and it communicates something kind of weird, that when two objects are some distance away, the potential energy they store is negative. If you have taken AP Chem, or you're going to take AP Chem next year, or you're going to take chemistry in college, you will actually have to get a little familiar with negative energies. In science, we have negative energies, or negative potential energies, when the objects are bound to one another in some way. And so you would see this in chemistry with like electron energies in an atom. They're always negative energy values because the maximum amount of energy that an electron can store with an atom is actually no energy at all. If they are not bound to one another, then there's no energy there. So this is gravitational potential energy would actually trend toward 0 as the value of r trends toward infinity. And so that's the only amount of reasoning that I give here, is why there's a negative. Why it's gmm over r is a whole other story that we probably won't talk about in this course. I'm going to backtrack a bit. This equation is good for anywhere in space for two objects. So this could be like two astronauts, but it's usually going to be like a planet and a satellite, or a planet and a star, or something like that. This equation gives a really interesting graph because it's negative and it's an inverse relationship between energy and the distance. And so the graph ends up looking like this, where the closer objects get, the less energy they have, and that energy increases to a maximum value of 0 if the objects are infinitely far apart. And so I just want to show you the only really, like the single way that I've seen this equation pop up. If we have three objects that are separated by the same distance from one another, in other words, their centers of mass are at the corners of a equilateral triangle, we can calculate the total gravitational potential energy between them. This is three pairs of objects. And so the way this works is you would just take this equation, negative g mm over r, and you'd apply it to every pair of objects, because this equation has two masses in it. So we'll do these two first. The gravitational potential energy between them would be negative g big M times big M over big R. Now we'll do the top left and bottom left. Their gravitational potential energy would be negative g big M 2 big M over big R. And then if I do the bottom left and the right, I have negative g 2 big M times big M over R. And if I add that up, I get a really big negative number, or a bigger negative number. The grand total potential energy for these three things is negative big G big M squared over R. And that's really it. So I wouldn't pay too much mind of this equation. It does exist and you can use it, and it also describes potential energy, but only for things in space. Thank you.